briefly, so we have several DPDs because on this diagram, you can trace the line with the spin and helicity carried by the nucleons and the quarks. So in the end, at leading twist, you have 8 GPDs. The first 4 usual ones, what I would say, are HE, HT, and ET, and are called the 4 chiral even GPDs. And then we have 4 chiral odd GPDs, which are called also transversity GPDs, for which you have an helicity flip of the quark that will interact with the virtual photon. So GPDs are extremely useful to determine and study, for instance, the total angular momentum of quarks inside the nucleon. So for instance, you have the G-sum rule that will relate the first moment of the sum of GPD H and E to the total angular momentum of quarks. Moreover, if you do a Fourier transform, for instance, of the GPD H, you can obtain the distribution of in the transversal plane of parton as a function of their longitudinal momentum. Finally, GPDs also are functions that can be used as comparison with theoretical computation. So DVCS, you have this virtual photon that will be kind of absorbed by the quark. So this virtual photon, as I said earlier, is exchanged with an incoming lepton. Now, the final step for DVCS is a real photon that has been emitted. And this real photon can also be produced by either the incoming lepton or the outgoing lepton, and this process is called the Bethe-Heitler. So experimentally, what we measure is not only DVCS, but is the quantum superposition of deeply virtual quantum scattering and Bethe-Heitler. Therefore, the cross-section we measure is proportional to the sum of the squared amplitude of both processes plus an interference term. I will introduce the last variable, kinematic variable, which is an angle, which is called the angle phi. So you can see a drawing on the bottom right of the slide. And this angle phi is the angle between what we call the leptonic plane, defined with the scattered electron and the virtual photon, and the hadronic plane defined by the virtual photon and the real photon that is emitted. And so our goal is to measure the cross-section of photon production, if possible, differential in these 4 kinematical variables that are Q squared, Birken X, T, and phi. So here you have an example of what on the right of unpolarized cross-section and beam helicity dependent cross-section. So this cross-section exhibits a strong dependence along this angle phi. And usually, if one wants to extract information about the Compton form factors, which are the complex integrals of GPDs, one needs to study the harmonics inside the cross-sections. So for instance, if you look at the constant harmonics carried by the DVCS square term, you can see that you have information about quadratic term about Compton form factor. So modulus, for instance, here of H or H tilde. Now, the interference term will mostly carry a first harmonic in cos phi in the unpolarized cross-section, and this is where this is the reason why we call DVCS, well, photon electroproduction, a golden channel, because unlike DVMP, through this interference with the Bethe-Heitler, we access real part and imaginary part of the Compton form factor. So for instance, the cos phi harmonics carried by the interference give us information about the real part of Compton form factor H and H tilde. Here, F1 and F2 are the elastic form factors that are coming from the interference with the Bethe-Heitler. Concerning the beam helicity dependent cross-section, you get information about the imaginary part of the Compton form factors. And finally, here, this was only for unpolarized target, but for instance, if you decide to look at longitudinally polarized target, you can see that you switch your sensitivity between the Compton form factor imaginary part of H and imaginary part of H tilde. So by playing with the polarization of the target, you get a privileged access to different Compton form factors. So what have we collected so far? So this, I need to update maybe this plot because it's not up to date, but you can see that we are trying as hadronic physicists to look at the proton on the very, very wide range in X Birken and Q square. So we have some colliders data that measured some cross-section differential only in T or some charge asymmetries. Then we have a huge gap in X Birken between 10 to the minus 3 to 10 to the minus 5, 10 to the minus 2, until we reach the region that was covered by Hermes and will be covered by Compass. So you see that Hermes here did a pretty great job because at some point they played with almost all the combination of polarization for the beam and target. And they measure asymmetries. And finally, then you have another gap until you enter the valence region, so above 10 to the minus 1 for Birken X, where it is the part that we cover here at JLab. So Class and Ole released data concerning asymmetries for beam helicity dependent or longitudinally polarized target. And Ole also released point for cross sections. And now the game to really constrain the GPDs is to fill all this phase space with as many observables as we can. So here the goal for class 12 will be, thanks to the upgrade of JLab, to fill the gap between the Hermes point and the JLab 6GV data. So class 12 is a very unique place to study the GPDs. So for instance, in class 12, you can use the large acceptance to explore this new terra incognita that has opened the 12GeV upgrade. Moreover, class 12 is an upgrade of class in order to reach higher luminosity. So we have a much better statistical accuracy. Now, if you look into the research program associated to DVCS on Proton inside with class 12, it's very rich. So for instance, as I told you, we would like to play with as many combinations between the polarization of the beam and the polarization of the target. And we have a lot of run groups that will cover all these combinations. So for instance, we have run group A and K that have a longitudinally polarized beam on an unpolarized target, and they play with the beam energy to try to perform a Rosenbluth separation. We have run group C that will have a longitudinally polarized target. And in the end, we also have run group H that is planned to run with a transversally polarized target. What you can also use is neutron data because you conveniently play with the isospin symmetry, but also you change the form factors of the nucleon. That will also help you to access different Compton form factors. And I invite you to follow the next talk by Sylvia about neutron DVCS. But this neutron program has a dedicated run group, which is run group B and also C, because we have some neutron longitudinally polarized. And finally, we have also the plan to have to take data with a positron beam. So this has been this is a proposal that will be in front of the next pack and hopefully will be accepted. And when you look into that, you realize that class 12 will have the first complete GPD experimental program ever run, because we have all polarization, all kind of lepton beam, and also neutron data. So this is some picture of class 12. So if you look at the top picture, it is a side view of class 12. So the beam is coming from the right and exiting from the left. So in the middle, you can see so what looks like kind of vertically, I'm sorry for the word flying saucer, is what you call the high threshold Cherenkov for electron PID. And on the left of this HTCC, drift chambers and calorimeters and time of flight. Now, a bit before this Cherenkov, you have the central detector package. So you have a 5 Tesla solenoid, and inside this 5 Tesla solenoid, you can look at the picture on the bottom now. We have detectors. So we have first a tracker, so 2 trackers, a silicon tracker and a micromegas tracker that can be conveniently pull out or push inside the solenoid. And you can see a lot of PMTs surrounding the tracker. And the first inner ring of PMTs is the central time of flight, and the outer ring is the central neutron detector. So to study DVCS in class 12, one must look at all detectors in class 12. So for instance, the electron will scatter off the proton, and you can see on the bottom right a drawing where you have the electron that will go inside the torus magnetic field, go through drift chambers for tracking, and reach at the end an electromagnetic calorimeter for particle identification. Concerning the photon can be detected either in the electromagnetic calorimeter at the very end of class 12 or close to the beamline and in front of the first drift chambers. We have a small calorimeter in PBW4 that we call FTCal that can detect also real photon emitted close to the beamline. And finally, the proton is either detected as well in the drift chamber or inside the central detector package where the proton is going through the silicon tracker. So here I am commenting the left, bottom left plot. So the first 3 layers are in fact silicium vertex tracker, and then you have 6 layers with green crosses. That is a micromegas tracker. And then the particle identification is provided by the central time of flight. So to detect, again, all the particles, depending on Q squared, T, and phi, the particle of a DVCS event are going in any part of class 12. And so one must really know all detectors to extract observables with good accuracy. So once you have cleanly identified electron, proton, and photons, you have a set of exclusivity variables to ensure the exclusivity. So on the top left, what we have is a missing mass squared associated to EP gives EP gamma X. So one expects, since we are supposed to detect all the particles of the final state, X should be centered to 0. Now, if at some point you miss a photon, since the mass of the photon is also 0, you will still expect to have background centered on 0 for the missing mass. So you look also at the missing energy. And the missing energy must also be close to 0. But you can also look at the missing mass EP gives E gamma X, for which in that case you miss the proton and you want to have a missing mass that is centered to the mass of the proton. We have another exclusivity variable which is on the bottom left called cone angle, which is in fact the angle between the real photon that you have detected and the expected proton when you look at the scattered electron and the recalled proton that you have detected. And finally, you can also look at the missing transverse momentum of the reaction EP gives EP gamma X. So I will explain it a bit later, but even if you cut on all these variables, there will still be some irreducible pi zeros contaminating your DVCS sample. So I will show you some result that has been shown last year at DMP. So here it is, it will be beam spin asymmetry on unpolarized proton with a lepton beam energy at 7.5 GeV. So on the top row, you can see the distribution of momentum for the scattered electron versus the scattering angle. So you can see that the scattered electron momentum can go up to 5 GeV. and the scattered electrons are mostly detected in the forward package between 10 to 30 degrees. Concerning the middle, show you the momentum versus angle distribution for the real photon. So here you have two parts. First part for the that are above 5 degrees up to 30 degrees, where in fact the photon is detected inside the electromagnetic calorimeter, detecting as well the electron. But you have also a part at small angle below 5 degrees, where in fact it is a small calorimeter close to the beamline in PBW4. And you can see that also it detects a lot of photon as well. And finally, the proton. You have a proton that are detected at fairly large angle compared to the two other particles, the scattering lepton, the scattered lepton and the photon, because the proton is detected in a range for of angle between 30 to 70 degrees. So you can see on the right the raw beam spin asymmetry that we have shown last year. This beam spin asymmetry, we qualified it as raw because we did not have time at that moment to make the pi0 subtraction. So we still have some contamination inside this sample, but stay tuned because also we will go through pass one for run group K, and once the pass one is performed, we'll have, since we have all the script, we'll have really fresh and brand new data. Concerning run group A, so once again, you apply the exclusivity cut. You can look at the electron momentum versus theta distribution for both, well, for the three particle electrons, photons, and protons. So you can try to compare them, but they are fairly similar, unless since we are now with a lepton beam energy at 10.6 GeV, the scattered electron can have momentum up to 8 GeV. Concerning the photons, you can see that we have photons that may have an energy up to almost 10 GeV. You can still see also the two parts, depending on where the photon is detected in the calorimeter. So you have a low angle photons below 5 degrees and detected in the FT cal, and in the big electromagnetic calorimeter, the photons above 5 degrees. And you have the proton, and here you can see that it is illustrating what I was telling you. Proton may be detected between 70 degrees up to, you can see that it goes up to 5 degrees. So as soon as you go below 40 degrees, the proton is not sent inside the central tracker, but inside the drift chambers. So as I told you, we have some, once we have perform cut on the exclusivity variable, we still have some contamination from pi0. This contamination is mainly produced by exclusive pi0 because of the very light mass of the pi0. The energy, the momentum of the pi0 is very close to the DVCS energy. And then the pi0 will decay into two photons. Depending on the symmetry of the decay, we'll have the momentum of the pi0 will be shared between the two photons. And if you have a very asymmetric decay with respect to the pi0 momentum, one photon will inherit almost all the pi0 momentum and so be misidentified as a DVCS event because it will have a very, very high energy. So basically, to estimate this pi0 contamination, one must estimate by Monte Carlo simulation the phase space of decay from a pion that will induce a misidentification as a DVCS event, and then to normalize this likelihood, you look into your data to see how many pi0 with two photons you have detected. So you can see on the bottom left Q2 Birkenex phase space with a preliminary binning. You can see that we can reach up to 10 to 12, well, almost 11 GeV square for Q square, and we are having data from Birkenex between 0.05 to approximately 0.72. And on the right, you can see for the same beams the missing mass spectrum. So the black one is for your data, and the red one are the estimated pi-0 contamination that we have. So what you can see is that concerning the beta-Eckler DVCS statistic, it gets larger when you're looking at low Q-square and low Birkenex. Looking at the pi-0 contamination, well, you can see that the pi-0 contamination seems to increase as Birkenex is increasing as well. So this pi-0 contamination is important to subtract, especially since when you have high pi-0 contamination, your cross-section for beta-Eckler DVCS is not as high as you can get in other beams. And so you can compute the asymmetry, and once you have subtracted this pi-0 contamination, and here I can show you now, bottom right, the asymmetries associated to the preliminary binning on the left that we have shown last year at DNP. So what you can see is that if you increase Birkenex, usually it seems that your asymmetry is getting smaller. So it is interesting also, maybe I forgot to mention that the polarization of our incoming electron was very high. It was about 85% for both run group A, so 10.6 GeV, and run group K, 7.5 GeV. And I arrived to my conclusion. So as I told you, the results in this presentation were shown at last DNP, but for PACE, we performed PAS1 reconstruction for RGA data, and we have made much progress on the analysis. And stay tuned, because we really planned for the next DNP meeting to show updated results on a much larger statistic. It will be at least an order of magnitude larger than what I have shown you today. The delicate point for DVCS analysis is really to subtract this pi-0 contamination, but this step has been performed and validated so far. So now what's left would be to refine the binning according to the statistic we have reconstructed, and do some proper computation of bin center and radiative correction also to perform as well. As I have shown, class 12 in the next year will carry out, I said may, because it depends also because we have PAC and Jeopardy, but I'm sure it's only a formality. So we'll carry out the most complete DVCS program ever. And I just want to finish with a great thanks to the PhD students that are committed in this analysis effort. We have currently 4 PhD students that are looking at all data we have collected so far. So Guillaume Christians for run group A and Sang-Baek Lee, Josh Artem Tan for IGK, and finally Catherine Price for run group B. So thank you very much.
For the very complete talk. We don't have any questions in the question box, and we're a little behind on the schedule, so I think if possible we can go on to from the proton to the neutron in the same light, and thank you very much. And is Sylvia?
Yes, hello.
We can hear you.
Yeah, do you see my screen?
Yes.
And do you hear me?
Yes.
Okay, thank you very much. Okay, so thanks a lot to Maxime, who made a very nice introduction to the GPD program, especially for the class 12 collaboration, and he mentioned the Proton program, and now I'm going to focus on deeply virtual quantum scattering on the neutron. So I will not really go in the detail of the theoretical introduction. I will just remind a few points, as Maxime has already been describing in detail the issue. So The main point I wanted to point out that are going to come back in the rest of the talk are the fact that basically measuring generalized Parton distribution is important for several reasons. There are two main properties that we like to put forward. One is the possibility to extract the contribution to the quarks to the total angular momentum of the nucleon with the G-sum rule, and the other one is the possibility to do the tomography of the neutron, of the nucleon, by correlating the distribution in the longitudinal momentum dimension and the transverse position of the parton in the nucleon. So these are important issues that we want to tackle, but there is a complexity behind, and this complexity is due to the fact that even if we restrict ourselves to the leading order, twist 2 and chiral even GPDs only, we still have 4 GPDs, and we have 4 GPDs for each flavor of the quarks, and they depend on 3 kinematic variables. So in order to really sample the kinematic dependence of the GPDs and access all of them, we really need to have a full experimental program, and this experimental program has not to be only focused on the proton, but it also has to be on neutron target for different reasons. As Maxime said, what we access via DVCS is not directly the GPDs, but is combinations of these quantum form factors, which appear with different weights in the expression of the different observables that we can see, that we can measure. And basically, depending on which target we use, either the proton or the neutron, and which observable we extract, we can be sensitive to different combinations of these quantum form factors. So, for instance, the beam spin asymmetry for the proton target is particularly sensitive to the H-related quantum form factors for the proton, while the beam spin asymmetry for a neutron target is sensitive to the E quantum form factor of the neutron. So basically, if we want to extract quark dependence and the different GPDs, we need to measure several observables and for the different targets. So if we look at the situation of published data on Proton DVCS, I made this table of different kind of observables that were measured, and also there are all the moments that were extracted according to the notation of the Hermes collaboration. So the higher statistic results are the black ones coming from the class collaboration from 6GeV data, and we have a lot of moments of different observables that were also extracted by the Hermes. So with all this data, a lot of phenomenology has been carried out, and we managed to have a first model-dependent extraction of what we call the tomography of the proton, which is this image here describing the momentum distribution of the partons on the x-axis and their transverse position on the y-axis. So this basically tell us that the valence quarks that have the higher momentum are focused in the center of the proton, while the C quarks are spread around its boundaries. So basically, this is already something we were able to say on the proton because of this wealth of data. And as Maxime said, there are several other observables on Proton DVCS that are planned to be measured with the 12GeV at Jefferson Lab. But we need the neutron. We need the neutron because, as I said, if we want to extract the flavor dependency of the different quarks in the GPDs, we have to combine observables measured on proton and neutron. And if we want to tackle the G-sum rule, we need to measure the GPD-E. And the GPD-E is quite elusive. In fact, if we look at Proton DVCS, the only observable that has a sensitivity to the eGPD is the transversely polarized target asymmetry, which has an equal sensitivity to H and to E. However, so far there has been only a very low statistic measurement from Hermes of this observable, and there are, I mean, the transverse polarized target is not yet a reality, at least for class 12. So on the other hand, the beam spin asymmetry for NDVCS has also a strong sensitivity to the GPD-E. It's another E because it's the E of the neutron. It's a different quark combination. But this is the observable that is, let's say, readily measurable with the strongest sensitivity to E. So there has been already, let's say, the interest of NDVCS has been brought up thanks to the measurements that were performed at 6 GeV in OLE. So OLE measured the scattering on a deuterium target, detecting the electron and the photon, and then reconstructing the NDVCS convoluted with the deuterium, coherent deuterium DVCS, subtracting proton hydrogen data from the deuterium data. So there have been two subsequent results. One of them just published from OLE, from analysis of 6 GeV data. The first result that was published in 2007 extracted the beam polarized cross-section difference for NDVCS, getting to the extraction of a combination of quantum form factor for the neutron that came out due to statistical and systematic uncertainty and the small size of the cross-section. This result was compatible with 0. It still helped to get a first model-dependent extraction of the angular momentum of the quarks U and D, and showed the importance of this channel for the GPD program. And recently there have been a new measurement that was published in Nature a couple of months ago of OLE from an analysis of 2010 data that were taken at 2 different beam energy, and this allowed a Rosenbluth-like separation, and it led to the first observation of a non-zero cross-section for NDVCS. And these data were also used to start a flavor separation of combination of quantum form factors. So this was done at one kinematic point in Q square and X Bjorken, and at 4 beams in T that you see here vertically, and 2 beam energies. And coming to the class 12 program, so there is the measurement that was labeled high impact from the PAC is the extraction of the beam spin asymmetry for neutron DVCS. The reason why the high impact was awarded is that this is the most sensitive observable to the GPD-E. And the way class 12 is measuring this is in a fully exclusive final state way. We are in fact detecting the active neutron as well as the photon and the scattered electron. And to detect the active neutron, we have built in addition a central neutron detector to class 12. So this is just the old projections that were in the original proposal that basically give you an idea of the kinematic coverage that class 12 can allow. These are each of these rectangles is a phi distribution for a T-beam, and everything is plotted as a function of Q square and X. And this is the place where the OLE 6 GeV measurements are, and this is the extent of the class 12 kinematic reach. So this experiment NDVCS was included in a run group, as it's done with class 12. This is run group B that comprises a set of experiments for electroproduction on deuterium target. And basically, there are experiments covering all the multidimensional structure function measurement for the neutron inside a deuterium target, as well as there is an experiment of J-psi photoproduction and also experiment on short-range correlation. So roughly first half of the run group B experiment ran during last year in 2019 in 3 different run periods. one that we call the spring run between February and March, and then we had the fall run in the first part of December and the winter run in January. In total, this comes up to 39 PAC days, which corresponds to 43% of the approved runtime that was 90 PAC days. In total, we collected 43 billion triggers on 3 different settings of electron beam energy. And we had data at 10.6, at 10.2, and 10.4 GeV, and part of the 10.4 GeV were taken with outbending torus field, while the rest was with inbending field. We had an average beam polarization of about 86%. And we just submitted a proposal to the PAC for the Jeopardy in order to obtain the rest of the approved runtime. Basically, we requested the missing 51 days of beam that we haven't managed to take in this first part of the run. So Maxime has given a description of the class 12 detector, so I will just mention the specific extra pieces that were included for run group B. Okay, the baseline class 12 setup was also there for run RGA, and so were the reach and the forward tagger, and also the central neutron detector was already installed and tested during RGA. For RGB, we had the addition of the back angles neutron detector that was built specifically for the short-range correlation experiment that I mentioned earlier. So the central neutron detector is the component that is necessary for the NDVCS measurement and was built for that. So I will spend a few minutes talking about it. So the point of this detector was to detect the recalling neutron of NDVCS, and we expect these recalling neutrons to have angles in the backward region of class 12 and momenta around 500 MeVs. So the detector's requirements were to have about 150 picosecond on time resolution and less than 10% momentum resolution and a neutron detection efficiency of 10%. And we have used data to verify the performances of the detector. We have here a distribution of the timing resolution extracted from RGB data as a function of paddle, and in average we are at about 160 picosecond, which is slightly worse than the requirements. And we also managed to extract the neutron detection efficiency by using the RGA data on the proton and measuring the final state with a neutron and a pi plus and comparing the missing and detected neutron in the region of the central neutron detector. And this allowed us to extract the efficiency, which in the momentum region of interest, which is around 500 MeV, is 10% as expected for the CND. And here is just an overview of the data quality for the various subsystems for a subset of data of RGB, just to show you that all the detectors work fine. We have nice mass PID distributions for the forward time of flight, sampling fraction in the calorimeter, nice pi zero peak for the photons reconstructed in the EC, and alignment for the vertex distribution as a function of sector from the drift chambers, and the forward tagger nicely reconstructs pi zero, vertex from the central vertex tracker, and the CND also can do some charged particles PID in the center, and you see here the bands for the pions and the protons. So I will now show some results from for NDVCS. These results are coming from a subset of the spring data It's a set of data that we call the DNP cooking. Is the same, is the equivalent of what Maxime mentioned for the Proton. These data were reconstructed last summer, and it's 33 runs that constitute more or less 20% of the spring run statistics, which in the end it's about 3% of the whole originally approved beam time. So the calibrations and reconstruction for this data set was preliminary, and since then we have completed and improved all the calibrations, and we recently passed a review within the collaboration to do the full reconstruction pass on the spring data set, which is now ongoing. So these results are to be taken with a grain of salt, because soon there will be new updated and improved results, also with the higher statistics. Anyway, this is a first glance. So just a reminder, we're reconstructing the final state electron, neutron, and photon, applying particle identification of class 12. And the photons are both in the forward tagger and the forward calorimeter, and the neutrons are reconstructed in the central neutron detector and in the forward calorimeter. And we use the simulation of NDVCS on deuteron to help in selection of the final state, defining exclusivity cuts, and see the optimal detection topology. And just a glance at after the selection of the final state and the application of some what we call base cuts on the kinematics, the comparison between the data and the Monte Carlo for the kinematic distributions of electron, neutron, and photon in the bottom. One thing that the Monte Carlo tells us is that if we want to extract DVCS events, we should look at the cases, at the topology with the neutrons mainly in the central detector and the photons mainly in the forward tagger. That's where the majority of our events will be. And coming to the results, the way after the selection of the final state, we have a combination of several exclusivity variables that we look at, and guided by the Monte Carlo, we apply cuts and we select the final state. Here is an example of how the delta T distribution looks after application of exclusivity cuts on the other variables. And below, down here, you can see the kinematic distribution of the final selected sample of events. The average Q-square, it's about 2.2, and X-Bjorken 1.17, and minus T 0.49. And you have here the resulting beam spin asymmetry for NDVCS, integrated overall kinematics, overall detector topology. This is a raw and very preliminary beam spin asymmetry, and there is no pi-zero subtraction, and we are working on this aspect right now. We are also working on developing a veto for charged particles only based on the scintillators of the central detector of class 12 in order to remove some leftover proton contamination that there can be in our neutron sample due to holes in the acceptance of the central vertex tracker or overall inefficiency. So this result is preliminary, is to be taken with a grain of salt. It's nice to see that there is a signal and that we have extracted NDVCS final state. For a sanity check to make sure that we are doing things correctly, we use the same data set to extract proton DVCS on deuteron. So it's also a check that the illicit information is correct and the selection of the final state as well. So we used exactly the same kind of analysis, but instead of detecting a neutron, we detect a proton. And then we do the combination of exclusivity cuts, and we look at the beam spin asymmetry that you can see here. And it has the the expected distribution, the expected shape, and comparing it with the raw asymmetries for RGA, I think it is in the ballpark at the central kinematics. So another nice thing that this cross-check on PDVCS gave us is that the NDVCS and PDVCS yields seem to scale as expected, keeping into account the different expected cross-sections and the different detection efficiency for proton and neutron. And also for proton DVCS, we are working on pi-zero subtraction, because aside from checking that our helicity and data analysis is correct, this channel has also other interests. In itself, it's interesting as a starting point for the studies of nuclear medium effects on proton structure. There have been in class 12 recent measurements on helium-4 and of DVCS on the proton in the bound final state. So it's interesting to have it on deuteron as well. And it's also an important channel in order to evaluate the impact of final state interaction for NDVCS. We can use proton DVCS on deuteron and compare it to the PDVCS on free proton and have an idea of what the final state interaction in deuterium are and use them to correct NDVCS. So this first part of RGB has finished, and as I said, we'll pass through Jeopardy to get the second part. In the meantime, the NDVCS program at class 12 has other experiment in the pipeline. So we are aiming to measure target spin asymmetries, making an experiment with the longitudinally polarized target. We will measure singularly polarized and double spin target spin asymmetries. And the idea here is that combining these new observables along with the beam spin asymmetry will help us to put more constraints on the quantum form factor and be able to finally extract quantum form factor for the neutron eventually. So this experiment will use the same setup of the run group B, but will have a longitudinally polarized target, which is in the work at JLab. You see here it's not a drawing, it's an actual photo of the target insert. And the experiment is right now probably foreseen for 2022 due to it was expected for 2021, but probably due to the COVID delays, it's going to go a bit further on. And just to give you an idea of what we could achieve if we manage to complete the whole GPD program on the Proton, which includes many of the things that Maxime mentioned in his presentation, and the planned NDVCS program. Here it's just a result done with pseudo data, making projection of all the observables for PDVCS and NDVCS, and operating a fit to extract the CFF, and then a flavor separation to pass from nucleon CFF, here we have H and E, to quark CFF. So basically the purpose here is to show that the completion of the P and NDVCS class 12 program can help to get closer to the GSAM rule in a flavor separated way. So I get to my summary, and basically now we know a lot about the Proton. We have managed to provide a first idea of tomography, so we can think about flavor separation and the GSAM rule, and for this we need the neutron DVCS measurement. The importance of this measurement was shown by the Olay measurement at 6 GeV, and now with class 12 we can cover a vast phase space, and we can add the detection of the neutron and minimize the systematics in the selection of the final state. So we have 43% of the experiment that ran in 2091 using the central neutron detector, which performed according to the specification. And we have a first analysis on a preliminary set of data, and we have managed to extract the final state and have a very preliminary but promising raw BSA signal, and we are currently working on processing the whole statistics taken in 2019. And we have the polarized target experiment, and with the extraction of the neutron CFF that we'll obtain by combining the various observable, we can aim to flavor separation and the GSUM rule, which is the final goal of this program. I'm done. Thank you very much. Hello?
Will, we don't hear you.
But did you hear me?
Yes, absolutely. Wonderful talk.
Thank you very much, Lorelei.
Yeah, okay. So maybe Will is having some connection issues now.
Okay, I can look at the question.
Yeah, so we are running quite a bit late,
Okay.
I think, relative to schedule.
I'm looking at, you want me to answer to the questions or not?
Well, I think perhaps we'll skip to the questions. So the questions do allow you to type an answer in there.
Okay.
And I think in the interest of time, maybe we should move on to the next talk.
Thank you.
Thank you very much for the very nice presentation, Sylvia. So, Wen, are you able to share your screen?
I think so. Can you see me?
Yes, we have the screen. We don't have you on video, but we do have the screen.
Okay. Right. Okay. All right.
Can you click hide on the bar at the very top of the screen?
Oh, I see. Okay.
Slides. Thank you.
All right. Okay, so I'll get started. I'm going to try to put a timer and keep everything on time. It's working now. No. Okay. So thank you for the organizer for inviting me to give this talk. And today I'm going to talk to you about some of the latest calculation related to the Proton distribution function. I'll be mainly focused on just one-dimensional calculation for now, just because there are really not enough time to cover a lot of calculations. So I will start with just give everybody a few review about how you read the latest QCD numbers in general, and then the calculations. And then I just want to remind everybody that the latest calculation does have certain systematics. So I will mention that as I go along, and I will get to the main points of this talk. I was asked to focus on the Birken-Ashe dependence, and there are actually a lot of work related to the nucleon Proton distribution function, especially the one from the mesons and the one from the pseudo PDF and quasi PDF. And I want to also mention the Meson PDF a little bit if I have time. And there's just a lot of latest calculation going on in these topics. And finally, if I can, I'd like to mention a little bit about the Meson distribution amplitude, which is related to the wave function and some of the original mass that people are really interested in EIC. And I particularly like to focus a little bit about some of the latest technology we try to implementing the machine learning to extract some of these distribution functions. So for some of the youngster who is not familiar with the latest QCD, it's actually a theoretical tool to try to investigating the strong coupling region, which is mainly the low energy, a few GeV or less, using the basically try to study it through the computational point of view. And so what you start with is very similar to what you learn in the theory classes. You have a certain action. So in this case, we have fermions and gauge degree of freedom. And because we study QCD, so we mainly look at the quarks and gluon, which is our main fields. And then if you can write down the observable, in principle, you can take this path integral, and then you can calculate specific physical observable of your interest. And we will, instead of doing this in Euclidean Minkowski space, we will be doing this in Euclidean space so that we can put this problem on the computer and we can numerically evaluate this. And so we have like the continuum theory, we also have Planck mass parameters as a dependence. And so in real life, you can fix that to a specific number. On the latest QCD, you can actually vary that quantity because it's part of the variables of the fermion actions. And then we had to do something slightly different from the continuum, which we impose a ultraviolet cutoff, which is basically give you the smallest, highest energy cutoff of the theory. And so you can think about this as more like a resolution, right? So you can study a system, you have different resolution. The smaller resolution, the better. But on the other hand, you also, just like picture, right? You have higher pixels, the data file get really large and harder for the computer to deal with. So there's certain trade-off we have to worry about. And we also we cannot simulate infinity degree of freedom on the computers. So we had to have some kind of infrared cutoff. That means that the system we study will have a maximum box size, and then we will be using periodic boundary condition or different boundary condition, depends on the physicist interest. And at the end of the day, once we did all this, we need to make sure that if our Planck mass is not directly calculate the physical pion mass, we had to probably do multiple calculation and extrapolate to the physical pion mass. And then you have these resolutions, and you have to either be sure that the physics is not affected by this resolution, your choice, or you have to do multiple latest resolution and extrapolate to 0 to do the best job you can. And similarly with the boxes as well. So we need to remove all this assumption we put in, and then only then we can, compare with experiment numbers or make prediction from the QCD point of view. Right. So this is not actually new. This has been around for a while, and so while we haven't really solved the QCD, it sounds very promising. And the problem is the progress does actually limit a lot by the computational resources, like many of the today's numerical problems. So just give you an idea, in the 1980s, this is kind of the state of the art computer game you can play on, probably a computer larger than the DEX you can put. So today you can have this tiny device even on your phone of the PSP or something that you can have a much better resolution and a more computational thing. And so this is actually benefit our field as well, that people can start to study something more realistic from very, very tiny boxes and very poor resolution to today. We can do a lot more realistic calculation. But just with the hardware is advanced, it's not actually going to be enough for us. And so a lot of our colleagues have been collaborating with applied mathematicians or computational scientists, which actually help us to advance some of the algorithm we use. Therefore, we are able to, in today's calculation, you'll probably hear people mention physical pion mass examples. It's become a reality. Without this, we might be still a few years behind. And so that's very important. And another thing I like to acknowledge as well is we also basically we use a lot of software that's been maintained and tested and ported from different computers. Computers have evolved throughout the year. They change a lot. So teams like latest team, such as Robert Edwards and Balen Yu and Frank Winter, they have been spending a lot of time maintaining a specific QC software that many people, not just within US, but also around the world, have been using them, and they have been very beneficial for the development of the fields as well. And so what do you need when you want to calculate a hadron structure on the lattice? And so you usually will start with picking up a QCD vacuum. And as you might have known, that the QCD is actually very dynamic. So what we are doing here is literally we will have to capture the snapshot of the QCD. So you can think about it like we are taking pictures. We are taking multiple pictures, and we're taking enough of them, and then we stack them together. You'll be able to simulate like a real QCD and then the dynamics. So it's very important to have. We had to, sometimes we call trajectory. You want to simulate long enough so you can actually capture all the important feature of the QCD. And this is sometimes, but to generate this QCD vacuum is one of the most expensive thing to do under this QCD. So the big collaboration like the JLUO lattice QCD group or the other US collaboration like Milk, they have a big, really large size of the collaborators that are able to actually and get sufficient computational resources to do this kind of calculations. And often there you have, because QCD have quarks and gluons, and so you kind of have to choose what kind of action that you use. And so the gauge action, the fermion action, sometimes you hear them. And you have also choice to see how many type of quark flavor you want to put in the QCD. You can put up and down, and we often do, because up quark and down quark mass is so similar. So right now, still a lot of calculation in physical power mass, we still have up quark mass degenerated down quark mass. You can add a strange quark mass, which is 2 + 1, or even add a dynamic neutron, which is 2 + 1 + 1, etc. And then you have a choice of the quark masses, which indicate as a pion masses here. You can choose your resolution, etc. So a lot of those parameters are being decided when you pick a QCD vacuum. And next, then we can try to study the observable of interest. So here I'm just going to have a very simple 2-dimensional picture, but remember all this calculation is done in 4-dimensional calculation. So you have Euclidean time, and then you say, for example, I want to study a nucleon, so I will create a nucleon at specific source locations, and I will calculate something called quark propagators, and then I will kind of annihilate it in another Euclidean time. And before it dies, then I will try to plug in that like a probe, which is the operator I put in here, and I want to study as much as I can so that I can kind of make up the feature of this particular matrix ornament that I can study from analysis. And so they are having a lot of study. If you read any of the latest calculations or papers, there will be a lot of study mentioning something called excited state systematic. And so this is something that people have troubled about 10 years ago due to the limited computational resources that because it's much, much harder to calculate. So you start to put the nucleon farther and farther away, and you can see something at the lower corner picture here. As you go farther and farther away, the data actually get a lot noisier very quickly. So one often had to make some kind of call about, how far can you go, and you try to do the best analysis you can. But you can see if you don't do a proper analysis, it's very likely to get the answer wrong. For example, if you only have a very small separation about 0.96 Fermi in this particular parameter choices, that if you try to estimate what the matrix ornament that can using ignore the excited state, you will get something kind of very wrong over down here. Very small error, but very wrong. And so there have been multiple techniques that latest people have been using to study and try to remove that. And here I show one of the examples that we call two-state analysis, where we specifically excited state degree of freedom, and then we fit in there so they can absorb some of the excited state signature and leave the ground state untouched. And as a result, you do see, so where the gray band here indicating the way the ground state is, and it is a lot noisier when you try to do this with the additional degree of freedom, right? Because data didn't change, so the error bucket larger. But what you can do, you find out as we started to put these two nucleons farther and farther away, they actually improve the signal, even though individual, what we call correlator here, actually the error increase. And if you're putting more of them, it can actually help you constrain this ground state better. So this is just one way of doing this, and there are many different ways that people can keep them under control. And so at the end of the day, when we do this, we had to repeat the same calculation on different type of the QCD snapshot. So that's where we get our statistical error, because we have particular example on each of the snapshot, so that we have a statistical error. And then different way of analyze this time dependence behavior that could contribute to certain systematic that we sometimes quoted in the calculations. And then there's also a different way to how we extrapolate to the continuum limit. And very often, for a long time, on the nucleon calculation, people only extrapolate to the physical power mass, or nowadays you can actually get direct physical power mass calculation. But there are also quantity like we have to also make sure the final value is not altering our answer, and the resolution is fine enough so that physics come out correctly. So I'm just going to be, because the nucleon calculation it's harder, and so I'm going to use this symbol, which is a monster living inside the nucleon, inside the latest three-dimensional illustration of the latest simulation, that to warn you that there are still certain systematic that's not under control, and especially a lot of time we didn't have a continuum limit properly taken, and so if you see the latest calculation discrete with each other because they didn't properly take this continuum limit, that's very normal, because you can have the systematic still coming from all these different factors. And this only go away, all different fermion and gauge action dependence only go away when you take the proper continuum limit. So people are using different actions so they can still get very different answers. And so just give you an idea what one need to do. So here is one of the quantity that the nucleon tensor charges, and basically it's just a zero moment of the transversely distributions. So it's one of the easier things to do. So what we need to do is we want to calculate multiple power masses, even though we have some physical power mass points. And then you want to calculate different volumes, and then different lattice spacing. At the end of the day, we do some kind of simultaneous extrapolations. And not only then, you can remove this, reliably remove this potential monster that could be living in the lattice calculations. And so there have been quite a lot of progress for the nucleon structures. So we have a flavor lattice average group that for a long time only reviewed the meson structure quantities. And in 2019, for the first time, they actually started including the nucleon quantity, because there are more and more calculations that satisfy that removing that lattice monster in the calculation. So what they do is they come up with some kind of thing like a consumer guide. If the rating is so, there are various different systematic that maybe for people outside the lattice QCD community doesn't quite know what they are. So we just kind of study them carefully. There's a group of representatives study them carefully and then rate according to how each of the systematic is under control. If it's good, then you get the star. And if it's not good, you get the red star. So at the end, that we can try to average different lattice QCD calculation. So if you are experimentalist of homology, just want to know how to, just want to use some of the latest number and then plugging into your model or other comparison, then you can just look at the report and pick out the average number, for example. Right. And then I just want to emphasize that even though we are starting seeing some of the impact of the lattice QCD calculation. For example, this is what I did with the Wallace and Alexei and Nabu in 2018, where we used the lattice QCD tensor charges to constrain the global analysis for the transversely distributions. And so here just again a function, we plug in the transverse up-quad and down-quad transversely functions as a function of x. The gray line here indicate where the x range of the data actually have. And so you see without the lattice constraint, we have this big yellow band because they have very limited data, and then try to pull out the whole range, and there's not a lot of constraint. But then with the lattice GT constraint, you can actually see it actually improve the distribution greatly. So this is one of the potential impact lattice can have to complementary, because GT itself doesn't tell us the X dependence, but by combining with experimental data and lattice calculation together, you can get a very nice up-quad and down-quad transversity that we haven't actually calculated them directly yet. But there's a limit on what lattice QCD have been doing for a long time. We calculate things called moments. And so I show you the tensor charges moment, which is when you have an equal to 1 in this case. But there are a lot of, actually what we want to pull out, a lot of Proton distribution, we are interested in the X dependence. And so there are a lot of, in principle, if you know enough moments, and then one can do an inverse problem to try to solve this individual different type of polarized PDF or the helicity distribution or transversity distribution. But there's been limited for a long time. We can only calculate a few moments and actually get really complicated. And the signal get really, really bad because on the lattice, we literally wear this rotational symmetry. And they, as everybody know in the undergrad classes, every time you wear the symmetry, there's a price to pay. And that the price is that they're having a long time. We cannot really, they've been, their second moment, third moment is really, really complicated to calculate. And even in recent year, a lot of calculations still focus on the first moment calculation. So in 2013, they have this new idea that from Shandong Ji, and then he recently had a very nice review paper on all this progress under these archive numbers, but he come out with a very interesting idea. So to calculate the X dependent directly. And so you can think about, so I'm just having a very naive cartoon here to kind of show you. So instead of, so what we want for the light cone distribution is kind of light up in the infinite moment frames and line up on this light cone axis. So by trying to calculate finite boosting quad distribution and replace the Wilson line, the light cone line into a spatial displacement Wilson line, one can do some very complicated field theory. Then you can approaching the light cone. So the larger the momentum you have, the smaller those correction is. And best part of that is we have been able to starting to calculate them using starting from 2013 resources, and today we have been doing a lot more. And so I'm going to start to talk about built-in X dependence, and I don't have a lot of time, so I'm going to rush it up a little bit. So I was specifically asked by the organizer to focus a little bit on the quasi-PDF and pseudo-PDF. So I'm going to start with that. So they actually both calculate very similar what we calculate in the nucleon matrix ornament, except we will have this operator slightly more complicated. Instead of a local plot, now you have a slightly more complicated operator that have a Wilson line in between them. And we actually, based on the latest, we will be studying the momentum. The matrix ornament we obtain from here will depend on the momentum, as well as we will be taking data as a function of this displacement length, which I call Z here. And so we will be doing this type of calculation. And with the pseudo PDF, once you obtain this, say, this matrix ornament, the very nice feature is you taking a ratio between non-zero PZ and zero PZ. And there are nice feature about this because the something very complicated procedure that takes us a few years to figure out randomization, it's cancel out. And there are also other nice features, and they have been working at very different Fourier transformations. So they will be looking at X dependence when they Fourier transform to the coordinate space, the momentum space, and the Z square dependence. With the quasi-PDF, one of the big hold up for a while is to figure out how to do the proper minimizations. And so, but once that's done, then it basically, and then this minimization procedure introduced additional minimization scale that we had to worry about and later remove them. But that's doable. And sometimes we form certain ratio with the Z equal to 0 to remove certain systematic. And then with Fourier transformation, at the fixed PZ, so you still got this PZ dependence and to the coordinate space, and then whatever we renormalize scale there is still there. And then there's an additional procedure that we can remove this particular dependence later on to match into the light cones. So there is a lot of similarity because we all calculate this particular quantity. And so we look at this in 2017 when we first figure out how to do the proper minimization for the quasi-PDF. And when we compare them, actually look very, they are very similar, and that's why people also kind of sometimes confused. So if you look at the matrix ornament as a function of Z, so I can have this displacement going positive or negative directions. And then we look at the pseudo-PDF ratio, they are actually very similar. And so it's really my personal point of view is when choosing different calculation is really the convenience, how the method is, how the calculation is set up for us to calculate. My group people have known me for using a lot of quasi-PDF. For us to calculate smaller momentum require additional work, and we can get this much longer displacement for free. And for most of the pseudo PDF, they would calculation will set up slightly differently. For them, the p equal to 0 is free, and there's some benefit in the matching as well. So it's just very different way to do it. But at the end of the day, basically what you are doing is have certain quantity that you can calculate on the lattice, and then you want to do the proper continuum limit, etc. But it's coupled with the PDF or even three-dimensional structure, the generalized Proton distribution in a very complicated kernel way. And so making this instruction a little bit more complicated. And I also want to mention that there's also a new method around this called section method. I'm going to call them in short LOSC later on. I also try to color coding different results. And there are other like hadronic tensor currents that I don't have time to cover, and a little bit on the nuclear correlation. They have less study, but they still have great potential. So what they have in common is this kernel is really complicated, so there's no direct inversion we can do. So there are certain times you have to do certain approximations. And so also they are different approach. So every group will have slightly different approach to how to extract this PDF. There are pros and cons. That will probably by its own talk. I'm running low on time, so I'm going to fast forward for this. And a lot of these different methods still require large N to be able to reach either large enough PZ or large enough ZPZ, so that you can actually get to the smaller X region. So most of the calculation today are focusing on getting the mid to large X region correctly. So the quasi-PDF have been doing this having applied to the nucleon PDF for a long time. So we started having the 2017 started having the physical pion mass calculations, and the ETMC also have one from the 2018. And both of this, in the earlier stage, we are not really using any of the parameterization scheme, which is, if you start to feed the data toward this form, you're going to come out something very similar to the global PDF. So we just try to see how when you are testing the method, see how well it works and see the certain similarity that coming out of that. And then in 2018, we have improved the calculation with larger momentums. And again, this not using any of the constraint we could, but we didn't. Just kind of see how the calculation works. Just kind of try to get a sense of how the calculation is doing. And to today, so this is coming out just earlier this month. So there are multiple different quasi and pseudo PDF calculations, and then and there's also this all extrapolate either directly at physical pion mass or extrapolate to the physical pion mass. And then there's a JLUO within the memory result, which is not exactly the quad distributions, but it's a balanced distribution. But like I say, that none of these they are all one single lattice spacing calculations, and there's still some discretization. There's some systematic not covered, but the results are actually quite similar, considering there's still other systematic in play, and they are quite, having the right shape with the other global fitting result. And then when we look at the C flavor asymmetry, and there that we kind of run into the big problem, we don't really see a significant C asymmetry anymore when we are doing this dynamical calculations. So there's something to explore here. And then there are also polarized structures. I'm running low on time. So I'm just going to show you here. And then similarly, we can do transversity as well. But with the polarized PDF, we only have the result from the quasi PDF so far. And so it'll be very interesting to see this from the pseudo PDF or other method as well. And so again, so they are still, again, the transverse distribution is still largely bounded by local experimental data. So program like Salt Lake and other experiment could in principle be able to constrain some of this attempting global fit result in the end. And then there are some attempt for doing the gluon structures. a relatively heavy pion mass. But one thing to point out is it's very hard calculation, and we still, at a very, very heavy quantum mass, we can see some good signal, but once you start to lower the quantum masses, it gets noisy very quickly. So it's still a problem to solve. And then we are able to see the first strange PDF as well. So this is one of those cases when they are not really a lot of good data, especially in recent years. So most of the strange dependence from the PDF being extracting from a very old experiment, there have been long debates on how good they are. In addition, most of the PDF analyzers have been assuming this for example, the strange quad symmetry, strange quad distribution to be the same as anti-quad distributions. And we kind of look at these particular quantities, and what we find is actually our latest data this is the real matrix ornament. If there's no such asymmetry, you see our result that's very close to zero, which is what we see. And then compare with the other PDF, analyze the CT18, assuming this particular symmetry, so they are exactly zero here. And then PDF has tried to implement some of the data and they get slightly different. And they are, so far our data kind of prefer this particular symmetry. And then they are being other systematic.
You have about 5 minutes left in your time slot, if you can manage
right.
that. Thank you.
Yeah. So there have been other systematic on the way, try to remove that. So I'm going to skip it, and they are different conclusions, so you guys can look at that. So I want to mention the Meson structures. They have been quite a lot of calculations, and there are a lot of interesting from EIC and other workshop that's talking about that. So for a long time, people have been trying to find out what the pion balance distributions, especially at the large exponents. And so there have been some past calculations in the last year. This is summarized in last year by Nickel. So they have been basically a different method, quasi-PDF, and the latest cross-section method, and they come out with roughly slightly different results. But all of this have been done using single examples, so obviously there are still quite a bit of the systematic in there. And then recently, earlier this year, there have been an update this calculation, and I have a proper physical pion mass extrapolations, and they come up with a very different exponent. Depends on how it's extrapolated, you come out with something that's close to 1 or close to in ideal cases. And then we repeat a very similar. We simultaneously also calculate the pion valence quad distributions and using different lattice spacing as well. And what we find is we be using the same. Okay, sorry, this is wrong. Oh, anyway, so we come up with something that's close to 1 as well. Sorry for the typo here. I'll fix it later. Yeah. And then we are also able to start to look at the K-on structure as well. So here is one of the common structure that everybody compare with the experiment from a long time ago. So show in this black data point, and our ratio was this green band. And so as many people have discussed this in the workshop that mentioned in Tanya's talk, as we find many different models have very different prediction for the strange quad distribution inside the K-on, but everybody come up with very similar ratio. So there will be great interest to improve some of this experimental data to be able to discern a very stable calculation. And we also working human try to improve some of the pion, the gluon PDF inside pion as well. So anyway, just try to show you roughly some of the quality data that we've been comparing. In 2018, we had this very noisy data. We cannot go very far in ZPZ, and that had limiting how we can extrapolate the gluon PDF. And we have been working on improvements, and my student JLUO fan, and we are able to kind of extend that a little bit. So stay tuned, we will have more results. And then lastly, 2 minutes, hopefully, I would like to mention quickly about the Meson DA calculation, and this is mainly my grad student Ray Zhang. So basically, what we are calculating, again, we have two lattice space, 2 pion mass. It's not a lot, but that's what we were trying to extrapolate them. We have 3 lattice spacing, and we are calculating basically a quark. So if in the case of the kaons, we will be calculate this type of diagram. We have a displacement at the ends, and then this actually helps us plotting the wave functions of the specific structure. So what we do slightly differently is we are trying to use in this case that we have a lot of trouble in the past to extrapolate reliably with the distribution in that inverse function I showed you earlier. And so what we do here differently, we use two different approaches. We're using one of the fitting approach like everybody else. And then we also try to use the machine learning to train a known, say we come up with different model of the distribution should look like, and we train the machine to recognize between the distribution in F space and what the distribution in the Z space. And then we testing various different model a few times before we apply the real latest data on them. So what we do is we also, before we do that, we try to test whether when we test whether this training is enough, we try to input very different function. It's not close to what we put in, and then we vary this very different sign form and see how well the machine, let's train network can recognize them. And it turned out once you get this, you can really reliably reconstructing this, and that's when we put in the latest number in there. And this is what we got at the end. There are a few tricks in between that we have detailed in the papers. But at the end, we actually find out this is a reconstruction from the machine learning, which is shown in the blue line here, and with the fits, etc. And so it actually turned out to be quite similar. Not too different, other than it's noisier and it's not as pretty because we did not really impose any particular form in this case. And so I think that's something really interesting. So we would like to kind of apply this to many other methods. And then here's just a summary result. I guess everybody can see on the website. So I'm running really late. I'm sorry about that. I'm just going to leave my conclusion here and like to then more collaboration, because we use a lot of lattices in they generated, and my grant that support my students and myself. Thank you.
Okay, thank you. Can you hear me?
Yes.
We have some questions, but I think in the interest of time, we should probably end the session and you can answer the questions in writing in the box. I think we have a break now for lunch until 1 o'clock. So we have 33 minutes for lunch, and we reconvene at 1 o'clock. And don't forget, the virtual poster session starts at 2:30. So thank you very much, and we'll see you in 33 minutes.